Hi Year 11 and welcome back to the next video in the Chemistry Paper 2, preparing you for Paper 2. This is the rates of reaction topic, and again this video is for higher tier and foundation tier, and I will tell you the difference between the higher and the foundation tier as we go through. But as you can see, we've got quite a few things to cover in this session, so we're going to talk about what rate of reaction actually means and how we would calculate it. And in particular, calculating it from a graph, because that comes up in both higher and foundation tier. We're then going to look at the 4 factors that can affect the rate of reaction and why they affect the rate of reaction. We're then going to look at collision theory and activation energy and how they link together, and then how these factors can affect that. And we're going to look at catalysts as well. And then as you can see, this is the required practical for paper 2, one of them anyway, which is all about how we change concentration and how that affects the rate of reaction. So we're going to look at 3 different methods and how we would actually go about working out the rate of reaction, because there's a few things we could potentially do. So I want to begin by just first of all reminding you that this is in no way stretch of imagination a real lesson. This is about going through the key content. If there's anything that you don't understand, please don't hesitate to email or speak to me in the lesson. The booklet is also attached with the video, so again I would suggest printing off the booklet and then annotating the booklet as we go through. So I want to first of all start by getting you to have a think, well, if I'm defining the term rate of reaction, what would I actually define it as? Okay, so just take a minute, think about the definition for rate of reaction, please. Okay, so if I was going to define the rate of reaction, I would define it potentially as 2 things. Okay, so I could either define it as how quickly the reactants are used up. Okay, so how quickly the reactants are used up. Or I could say it's how quickly the products form. So as you can see, I have time. Okay, so time is involved here for the rate of reaction. And if I'm looking at reactants, that could be, for example, mass of reactants going down, or it could be the production of a gas. So we're measuring how quickly it takes to make those products. So the products are formed. So these 2 things are usually an indication of how we would define the rate of reaction. So don't get confused by it as how fast it takes place, okay? So it's about how quickly the reactants are used up or how quickly the products are formed. Now, there's a calculation that can go with this. So basically, the rate of reaction, okay, could equal the amount of reactant used or the amount of product formed, depends on which specific reaction they're looking at. Okay, the amount of product formed divided by the time. And as such, they will have specific units to them. So for example, if I'm looking at a gas, and let's imagine the amount of reactant used was actually a gas, then I'd be looking at volume there, wouldn't I? So I would say that the amount of reactant as a gas would be centimeters cubed. Or if I was looking at the mass reducing, again, in that case, I would have the unit grams because that's us looking at mass. Time is usually always measured in seconds. So that means our rate of reaction units could therefore be centimeters cubed per second. Okay, so there's my volume 1. Or they could be grams per second, depending on whether I have a solid or not. You can also measure the amount of a product or reactant in moles. That is higher tier. So just be aware that for higher tier, the rate of reaction could also be measured in moles per second. So you'll know already about moles from the moles equals mass divided by MR equation, which we talked about in paper 1. So again, that could link, if I have mass, for example, it could link to the rate of reaction. But that is higher tier, so just be mindful of that. Now, when we look at calculating the rate of reaction, most of the time they will give it to you in a graph format. And you will have either the amount of product formed or the amount of reactant used on the y-axis, and you will have time on the x-axis. So here's my y-axis, here's my x-axis. So in this case, I'm looking at the amount of hydrogen produced. And as you can see, that's a volume measurement. So that it would be the amount of product formed. And if I wanted to work out the rate of reaction, I would divide it by the time. So dead easy to do, but for some reason, particularly on foundation tier, we struggle doing this. And this is all about manipulating the graph and making sure we can interpret the graph correctly. So as you can see, I've got time. And if they ask me to calculate the rate of reaction for 20 seconds, or they might say from 0 to 20 seconds, they will usually always give you one of them, okay? So you need to just be aware that they'll give you one of these in the question, and that's why reading the question, bugging the question is so important. So the question is asking me to calculate the rate of reaction for the first 20 seconds. So I go to my first 20 seconds, there's my time. I then go up to the line, and as you can see from the diagram, I'm then going to go across, and as you can see, that gives me 45 centimetres cubed of gas produced. So in order to calculate the rate of reaction from the equation we've just talked about, I would do 40 divided by 20. And that's obviously half, isn't it? So what's that going to give me? 40 divided by 20, that is going to give me 2. But again, I've got to think about my units. So I've got volume for my units here and seconds for my time. So that would be centimetres cubed per second. And that would be the rate of reaction. Now, they may also say to you, can you calculate the reaction for the first 30 seconds? Again, the principle is the same. I find the time, and I then go up, and I then go across. Again, I can see that that's 65, that time is 30. I plug it into the equation, and that would allow me to work out the rate. So very rarely have I seen it come up with you just asking you to calculate it. It's usually with a graph, and you have to therefore be able to calculate it from the graph. Okay, moving on. As I said earlier, moles can also link to rate. So the rate, this is again for higher tier only. So if your foundation tier, just fast forward through a little bit. But the rate of reaction can also be in moles per second. And that ties into, obviously, equations we looked at in paper 1, which is moles, MR, and mass. And you might, for example, be given the mass of reactants used, and you know what the substance is that you're using. You're given the time, so you take the mass and divide it by the time, and therefore, so mass and MR, sorry, you could then work out the moles, and therefore you could work out how many moles per second that specific mass would give you. So just be aware, that's what you essentially may be asked to do. You've also got volume potentially linked to moles here, haven't you, as well? Where you've got volume, moles, that can link to this specific equation as well. Okay, so volume, moles, and 24. Remember we talked about how 1 mole of a gas has a volume of 24 decimeters cubed. So again, you've got potentially volume involved here and mass, just like we talked about for reactants and products. We can then manipulate this equation to get the moles of that specific volume, and therefore we can work out the rate of reaction in moles per second. Okay, so just be mindful for higher tier, that potentially could come up as well. Now, you need to understand what the idea of collision theory is, and again, you need to be able to define collision theory. Usually it's linked to the 4 factors that can affect the rate of reaction, and you need to be talking about collisions and more importantly, the amount of successful collisions. So they're the kind of phrases you need to be using if you ever have to explain a pattern in a graph, for example. We're talking about the amount of successful collisions. So if I'm going to define collision theory, in other words, what I'm saying is particles need to have enough energy in order for them to collide and therefore react. So particles need to collide with enough energy if I want them to react. Now, we'll know from paper 1 that when we're talking about energy here, what we're actually talking about is this idea of activation, which is this energy that's required for particles to collide and therefore the reaction to start. So the collision frequency of reacting particles, so how often they will collide, basically dictates how fast the reaction is occurring. So if you have increased the number of collisions, that is going to increase the rate of reaction. And there are 4 factors that can cause that to occur. So we basically want to try to increase the rate of collisions in order to therefore increase the rate of reaction. And as you know, activation energy is all about the minimum amount of energy that particles need to react. And particles need that much energy to break the bonds in the reaction to start the reaction off, essentially. And if you increase the number of collisions, or you can, in fact, or the amount of energy the particles need to collide, then you'll increase the rate of reaction. So what am I starting to hint at? Well, I'm actually starting to hint at the 4 things that can basically affect the number of collisions. So that is concentration, temperature, concentration, temperature, surface area, and also a catalyst. And you need to be able to describe graphs, for example, showing the patterns of the rate of reaction, or you might be asked to explain why the graph has that specific pattern. So we're going to look at each of these 4 factors in turn. And as you can see, I've given you 4 diagrams. And we're going to go through and basically annotate each of these diagrams to explain how they affect the rate of reaction. So we'll start with concentration and how concentration affects the rate of reaction. I think that's probably the most straightforward one to understand. Essentially what we're saying here with concentration, so if you've got a more concentrated solution or amount of reactants, I can spell concentration, that'd be good. So more concentration, that essentially means there will be more particles. Okay, as you can see, I'm increasing the concentration in my picture. The amount of particles are therefore increasing. That's what concentration has to do with. And if I have more particles, will I have more successful collisions? Yes. So that's going to increase the amount of successful collisions. And if I have more successful collisions, what's going to happen to the rate of reaction? Well, that's going to increase the rate of reaction. So if I'm asked to describe how concentration affects the rate of reaction or explain a results, for example, so you often get the graph where you have time and, concentration increasing, rate of reaction increasing, and it goes up like that. And, or volume of gas, depends on what it actually is. The graph begins to increase, and as there's more particles, there's more successful collisions. And then we'll talk a little bit more about what happens here and here when we come to look more at the graph. But just be aware that concentration means more particles. So if there's more particles, there's more successful collisions. If there's more successful collisions, it means the rate of reaction will increase. The next factor is surface area, and this is the one that confuses people because we often think bigger means larger, but in this case what we're actually talking about is the surface area of the reactants in the reaction coming into contact with each other. So if I've got magnesium reacting with acid, then I'm talking about the surface area of the magnesium in that specific reaction. So the bigger something is, in this case then, it means it has a smaller surface area. So in other words, the amount of surface that is in contact with the acid would be less for a bigger substance. So for example, if I take a tablet and I try to dissolve a tablet in water, the bigger it is, the longer it will take to dissolve because I have got a smaller surface area. If, however, I take the same thing but in powder form, what I'm essentially doing is I'm making the surface area larger. So these guys have a larger surface area, and that could be powder, for example. So the smaller the particle size, that means more of the surface is in contact with the acid in this case, or the water if it was powder being dissolved in water. Therefore, the reaction, then the amount of successful collisions increases and the reaction speeds up. So what do I need to know? So larger surface area means that you're going to have more successful collisions. And if there's more successful collisions, that means that you'll increase the rate of reaction. Okay, so try not to get confused with that. The bigger something is, the smaller the surface area. The smaller something is, the larger the surface area. And larger surface area is good because that means you've got more successful collisions going on, and therefore the rate of reaction will increase. Temperature also can affect the rate of reaction. Again, this is about particles moving, and therefore we need to be using terms like kinetic energy. So if I essentially increase the temperature, I will be providing those particles with more kinetic energy. So increasing the temperature will increase the kinetic energy of the particles. So in other words, they are moving around more. And if they're moving around more, is the chances of them successfully colliding more? Yes. So that's going to increase the amount of successful collisions. And if we have more successful collisions, the rate of reaction will increase. Now, you will lose marks if you don't use the term kinetic energy. Okay, so be aware that temperature gives the particles energy, so therefore they are moving around more, so they have more kinetic energy. Chances of successful collisions will increase, and therefore the rate of reaction increases. You've then got catalysts. Now, you'll know from paper 1 that catalysts speed up reactions, okay, and make the reactions go faster. They're often transition metals, as you'll know from paper 1, but they speed up reactions because what they do is they lower the activation energy. So you can see here I've got a reaction profile with my reactants. I've got my activation energy here. The catalyst lowers that activation energy. So I'll draw another one here. So we'll know already that this is an exothermic reaction from paper 1. This here would be the normal activation energy. That's my reactants, that's my products. And what catalysts do is they provide an alternative pathway. So they actually lower the activation energy. So this is with the catalyst. And as such, the activation energy is less. And if we know already that for something to collide, they require a specific amount of energy, which is known as the activation energy. So if I make that energy less, that means that I'm going to therefore have more successful collisions and the rate of reaction would increase. So we're going to write increase rate of reaction because the particles don't need as much energy to collide, so therefore we'll have more collisions. So hopefully that's explained the 4 factors and how each of them affect the rate of reaction. Usually in the exam, they specifically focus in on one factor for a whole question, and they usually link to a practical of some kind. Now, we're going to look at the required practical that's around investigating how changes in concentration affect the rate of reaction. I'm going to show you 3 potential methods that you may get asked about. We'll talk a little bit about error because it's important that we're aware of error in this case. And then I'm going to talk about the graph because, again, you might be asked to describe the pattern in graphs and explain why that pattern happens. Or you might have to add a line for a higher concentration or a lower concentration or a larger surface area or a smaller surface area. So I'm going to show you how to do that. And then if you're higher tier, we're going to look at tangents and how you would calculate a tangent from a set of results. So we're going to look at the required practical now. So the first one we're going to look at is a method that requires a precipitation. So in other words, a solid will form in the liquid, and as a result, the solution goes cloudy. So as you can see here, I've got my scientist who's doing a chemical reaction. I've got a cross that's got sodium thiosulfate, and I'm adding acid to the sodium thiosulfate. I'm then timing how long it takes for that cross to disappear. And I've got a set of results where I've got my concentration of acid is increasing, and I've then got the time that it takes for the cross to disappear, and then I've used that information to calculate the rate of reaction. Okay, so you can see I've got a set of results already here. So you might be asked to describe a method that's linked to this practical. It's really straightforward. But I do want to point out a couple of things around variables, and I want to start with kid Sam. You'll know this already. Anytime you're talking about a required practical or a method, then you're thinking about your controls or what you keep the same. Your independent variable is what you are altering, so what you're changing the investigation, and the dependent is what you are measuring in the investigation. Now, you're often asked about the control variables around this specific practical, or you might get asked to plot a set of results. It just depends on what specific type of question comes up. But we're going to essentially write a method, and then we're going to describe the results so that you can at least do both depending on what the question asks. What I do want to point out, if you're asked about producing a method that would produce valid results, then that is always linked to repeat or your control variables. So you have to mention those things in your methods in order to get the mark for the idea of it being valid, a valid set of results from the method that you would collect. So you can see that they are changing the concentration. So the concentration is increased. So what they are changing, so what they are altering is my independent variable. So that's my independent variable, they're changing the concentration. And they're then measuring the time that it takes for the cross to disappear. So that is my dependent variable. So they're changing this and they're measuring that. And then they use this data to then calculate the rate of reaction, which in this case is 1 over time. And that then gives us the rate of reaction for this specific concentration. So let's look at a method for this then. So you can see we've got a set of equipment set up. I've got sodium thiosulfate solution, which I'm pouring into a conical flask. I've also got on below that conical flask, I've got a cross, and the cross is actually a control variable. So I'm going to actually put a list of control variables over here. So the thickness of the cross would be a control variable because I wouldn't want the cross to change in any way, shape or form. The volume of sodium thiosulfate that I add is got to be kept the same as well. Okay, sodium thiosulfate. You're also talking the volume of acid that you add would have to be the same. Okay. So again, if I'm describing a method that would produce valid results, I'm thinking about those things in that method. There's loads more, but they're the main ones that come up. So what are we doing here? So we're going to pour, I don't know, a fixed amount of, this is our method. So pour a fixed amount of sodium thiosulfate into a conical flask. Now you can actually state a specific amount, so you might say 25 centimetres cubed, but what we're hinting at here is that by it being a fixed amount, what we're saying is that is a control variable. I'm keeping it the same. Okay, so I pour a fixed amount of sodium thiosulfate into the conical flask, and then going to place the conical flask on top of the cross. So place conical flask. And again, I want to point out the valid element of this. Make sure the cross has the same thickness. Make sure you use the same cross each time. Okay, so I'm going to make sure I use the same cross each time. I'm then going to start with my first concentration. So 3 would be taking my first concentration of acid. So take 0.5 mole per decimeter cubed of acid at a fixed volume. So again, we could say 25 centimeter cubed, whatever it is. So we're taking our first concentration of acid at a fixed volume and add to the sodium thiosulfate start stop clock, and then we're going to time. I can't write at all today, guys. Time until cross disappears. And then, as I said, it's about valid, so we're going to repeat that procedure using the different concentrations. So really signpost to the examiner that you've took on board this idea of the results being valid. So again, maybe you might underline it saying control variable. Again, this would be my control variable here. A fixed amount of volume would be my control variable. So it's a good way of signposting to the examiners. So we then repeat the process. You might want to repeat it several times to get a mean, for example, which again would help produce more valid results. So we're going to repeat this using the different concentrations, and again, we'll time how long it takes the cross to disappear. I do want to point out that there is room for error here. Okay, so there is potential room for error. So for example, we might have a random error that could occur here, because obviously what I might deem as the cross disappearing and what you might deem as it disappearing may be different. So it's very subjective, and different people might not agree over the exact point that the cross disappears. So you can use this method to plot the rate of reaction graph from the results. So as you can see, I've got my concentration, I've got the rate of reaction, so I could actually plot a graph of the results of that. Do we notice that we get this sort of doubling effect? It's increasing by 2, so you can see that quite clearly on the pattern. So you might then have a graph of a set of results of this, and I'm going to leave that to look at when we come to look at the graphs, but hopefully you're happy with the methods. So a precipitate, remember, is a solid that is forming in the solution, and as a result the solution goes cloudy. Changing the concentration will make that process faster, so we know that already, because higher concentration, more successful collision, more particles, so therefore more successful collisions, and that's why it takes less time for the cross to disappear. I've seen this asked in the concept of temperature, where you heat the sodium thiosulfate solution up at different temperatures. Again, higher temperature, faster, particles are moving faster, greater, because they have greater kinetic energy, more successful collisions, the rate of reaction would be faster. So that's one method you could use to measure the rate of reaction. And again, I'll come to look at the results of these when we come to look at graphs. You may also be asked about another method, which is these two methods here. And again, in this case, we're talking a little bit about the production of a gas, because I've got a gas syringe that will be collecting the amount of gas produced. And the same here, I've got my delivery tube, and I'm then collecting the amount of gas produced. So you can see I've got time and I've got volume of gas produced. So again, this could be, for example, let's go for what? For magnesium plus hydrochloric acid. And it's going to make magnesium chloride plus hydrogen gas. And I'm then measuring the volume of gas that's produced. If I'm changing, I could be changing the concentration, I could be changing the temperature, I could be changing the surface area. But the principle of the method is what's key here. I'm not talking about the factor I'm changing. It's more about the method that I'm using to calculate what I could then use to calculate the rate of reaction. So here would be my reactants. I've got my conical flask that's attached to the gas syringe, and that gas syringe will change depending on the amount of product that I produce. So as you can see, at 20 seconds, I have made 28 centimeters cubed of gas. So do I have an amount of product produced? Yes. Do I have a time? Yes. Can I calculate the rate of reaction? I do. So I can take the volume and divide it by the time, and that would give me the rate of reaction at that specific time. But what do they normally ask about? So a couple of things to consider here is sometimes they get you to compare these methods. So can you see how I've got my gas syringe would be a better to use than a measuring cylinder, because here I'm actually introducing a systematic error, because potentially I could lose the gas between the gas being produced to the delivery tube and being collected in the measuring cylinder. So just be aware that sometimes that can occur and that could create a systematic error. But let's imagine I'm doing the same experiment for both reactions. Essentially what I'm measuring is the volume of gas produced. Okay, so the volume of gas that's produced in the reaction, the more gas given off, the faster the reaction. More gas in a certain amount of time equals faster reaction, and we know that already. Gas syringes are usually more accurate. Okay, so we're going to write that. So these are more accurate. Okay, and their volumes are accurate to the nearest centimeters cubed compared to a measuring cylinder, for example. You can take regular intervals of measurements. So you can see here I'm going up in 10 seconds. So you can take regular intervals. Take measurements at regular intervals. And therefore, as such, you can then plot a graph to show the reaction, which is what we're going to look at now. So hopefully you can realise that the gas syringe is more accurate. One, it's a closed system. The other, it's all to do with the fact that it can measure the volume to the nearest centimeters cubed more accurately than what a measuring cylinder can. Here you create systematic error because you've got the equipment's potentially causing bubbles of gas to escape. I've seen them asking that and how that can account for anomalies. But essentially, you can measure the volume of gas produced. Now, there's one more method that I'm conscious that I didn't actually put on the booklet, but there's another method you could potentially use to measure the rate of reaction, and that is to do with the change of mass. Okay, and again, that's to do with reactants being used up, okay, or potentially products being produced. But essentially, you're going to have a balance, and onto that balance, I'm going to have my reaction. You know I can't draw it to save myself, guys. And my reaction would be taking place in there, and that's got cotton wool is there. I've got my balance, which could potentially bring in zero error. Just be mindful of that. But essentially what we're doing is we can measure the speed of a reaction that produces a gas, and this can be measured in the form of a balance or mass balance. So as the gas is released from the reaction, so again I might have my... Okay, so I'm hoping I've got seamless editing here because my computer shut down for the last part. We left where we were talking about our third potential method we could use to measure the rate of reaction, which was this idea of change of mass. So if in my reaction I produce a gas, that gas could escape. And as you know, we can calculate the rate of reaction by the amount of product produced divided by time. So if my gas is escaping, my mass would go down. and that could be a way in which I could therefore go on to measure the rate of reaction. Okay, so this is potentially a way of doing it. So the quicker the reading on the balance drops, the faster the reaction would be. So let's say that. So quicker the mass on the balance drops. Okay, goes down, the faster the rate of reaction. Because I'm making more products, so therefore my reaction must be going faster. And it allows us to take regular time intervals. So we might, for example, take the mass every minute. And therefore I could then use that to plot a graph showing that the mass is decreasing over time because obviously the gas is escaping in the reaction. So if it was this reaction here, you can see I'm producing hydrogen, and that hydrogen gas would be escaping, and therefore the mass would go down. This is probably the most accurate of all the three methods that we've described on each of the different methods looked at, because this piece of apparatus equipment is actually very accurate. But the disadvantages you've got here is that we're releasing gas straight into the room, and sometimes we don't want to do that because it could be dangerous. And also it may be very negligible in terms of the amount of mass that would actually change. So things to take that into account. So that's essentially our sort of three methods we could use. So it's precipitation and going cloudy. So the sodium thiosulfate experiment. It's the measuring the volume of gas produced, either using a gas syringe or a delivery tube system with a measuring cylinder. Or it's the change in mass experiment. And again, we're measuring how the quicker the mass is reduced, the faster the rate of reaction. So again, it could indicate the rate of reaction. So they're all different techniques and methods you could use to measure the rate of reaction. But ultimately, we will end up with a graph, and most rate of reaction graphs will form this specific shape. And on both higher and foundation tier, you will be asked to describe the pattern in the graph. And I have talked about these kind of graphs to death. We always split the graph into three, and we describe what is happening in each section. And this is where a lot of you get mixed up with physics, so please try and avoid that. Okay, so you can see in the first sort of 10 to 12 seconds, the reaction is producing quite a large amount of gas. So therefore, I could say the reaction is happening quickly. So we've got a faster rate of reaction because I'm making more gas in that short period of time. And then we can notice over time that reaction, so the amount of gas I produce begins to slow down. So in other words, I'm not making as much gas over the next period of time, so the rate slows down. Okay, and then eventually I stop making gas altogether because it stays plateau, it levels out, and that's an indication that the reaction has stopped. So if you're asked to describe a graph like this, we're talking about breaking that graph into three sections and describing what is happening to the volume of gas, and then implying how that then is linked to rate of reaction. So making more gas over a short period of time, that tells me the reaction is fast. Then we're making less gas over a period of time, so therefore the reaction must have slowed down. And eventually when we don't make any more gas, it plateaus, levels off. So that's an indication that the reaction has stopped. They might, for example, ask you to plot the results of different concentrations. So this might be for, let's make this up. So this could be for a 1 molar concentration. It then says to do the same for a 2 molar concentration, keeping the volumes and everything else the same. So this is a higher concentration. So would I expect the rate of reaction to be faster? Yes. So the line itself would be steeper. So I know that that's the case if the reaction is faster, so higher concentration. So that could be the higher concentration. It could be a smaller surface area. It could be a higher temperature. Whatever it is will be in the question. But it will form a steeper line, okay? And it will then begin to level off at the same point because I'm not changing the amount of reactants, I'm just changing either the concentration or the temperature. So it will always level off at the same point. So again, I'm going to go up and then level off at the same point as what this one does. Now, if I half the amount of reactants, that's going to make half the amount of products. So even though the temperature might, say, for example, stay the same, but I've used half the amount of reactants, well, that would then level off half from whatever it is on this graph. If I'm talking about a lower concentration, a larger surface area, or a cooler temperature, then that means the line would go below it because the reaction would take longer. But still, just like with everything else, it will eventually level off, just like it did with the other line graph, because the only time that line will change is if I've changed the amount of reactants, and therefore I would make less or more products depending. Okay, so you might be asked to describe the graph, you might be asked to add to the graph to show a higher concentration or a lower concentration, but remember, it's all about joining up to where they form unless they have changed the overall amount of reactants. So you might then be asked to explain the pattern in the graph. So let's imagine I'm looking at concentration and I am measuring the volume of gas produced. So if I've got concentration and rate of reaction. Okay, so here would be my graph. Let's imagine this here would be for the first one. So again, I've got time and I've got volume of gas, and a higher concentration would be something like that, and a lower concentration would be something like that. So high, low. I might be asked to explain what's going on. So for a high concentration, I have more particles, so therefore more successful collisions, so therefore the rate of reaction increases faster. So that's why the line is steeper. Just like everything else though, the amount of reactants will get used up eventually, so the reaction begins to slow down and then stops. Okay, so in other words, I'm getting to that point quicker. If I've got a low concentration, that means I've got less particles, so therefore the less successful collisions, slower rate of reaction, which is why the line takes longer to reach that point. So you might be asked to explain the results of the experiment. But essentially, that is everything that you need to be able to do. I mean, again, you could calculate the rate of reaction. Again, you've got time and volume of gas. So you could do y divided by x would give me my rate of reaction. And again, the units would be, is it milliliters? Milliliters per second. And I'd use whatever they give me in the graph. But essentially for foundation tier, that is the rates of reaction topic. The last little thing we need to know for higher tier is often you are asked to measure the rate of reaction by measuring the gradient at various points on the line or the graph of results. And for that, you're going to need a ruler. Ta-da! Okay, so here's my ruler. It's like I prepared this or something. But you might be asked to draw the tangent onto the graph and then use that to calculate the rate of reaction, because you know that rate of reaction is y over x. So if I know the change in y and I know the change in x, I can then work out the overall rate of reaction, and drawing a tangent on the line allows me to do that. So just to make you aware, tangents essentially is all about the change in the y-axis divided by the change in the x-axis. And examiners will always give you, they might say initial rate of reaction, which is for a specific time. They often will give you the time that they want you to draw your tangent on. And I'm going to show you how to draw a tangent. So here is my y-axis, here's my x-axis. So if I am asked to find out the rate of reaction at a particular point, so they might say to you, calculate the rate of reaction from, in this case, I think that's what, 16 until 60, 74, I think that is. or as the line begins to curve, then, oh my goodness, there are processes that I would need to do. So essentially what I'm trying to find out is the gradient. So you need to find out the gradient of the line. And that's all about the slope of the curve. It might say, here I want to be able to draw a tangent for the slope of the curve. There's a couple of things you need to be aware of. So if you're asked to draw a tangent to the curve, you make sure it touches the curve at one point, but it doesn't cross the curve. Okay, so if you're asked to draw a tangent to the curve, then I can get my ruler, and here's where the line begins to curve. Okay, so again, the rules are quite simple. I want to touch the curve at one point only. I don't want to cross over the curve because that wouldn't be measuring the tangent. So I want to make sure that it basically touches the line where it curves, and I then draw my line. Okay, now that I've drawn my line, I can then work out the change in y. So that's y. And I can work out the change in x. And once I've worked out those two figures, I then put them into the equation. So again, I'm just going to point this out. So if you have asked to draw a tangent to the curve, you want to make sure that it touches the curve at one point, but it doesn't cross the line. Then you do your gradient, so you get your triangle on the go. So I then work out the change in y. So it's already been done here. So I can see that that gives me 39, take away 23 is going to give me my top number there, which would be 16. So my change in y, so that's the first part of my equation that I know. I then take the change in x. So again, I go down to the axes, and I see that that would be 74 take away 16. And that would then give me 58, which would be the change in x. So to work out the rate of reaction, I would do 16 divided by 58, and that's going to give me a rate of reaction of 0.28 centimeters cubed per second. Now, if you're asked to draw a tangent on this part of the curve, then again, the principle applies. You want to make sure that you draw your line where it touches the curve, but doesn't cross it. And then you can see here I've got a steeper y, so I've got more y, less x. So I'm making more gas in a short period of time, so I'd expect my rate of reaction to be faster. So hopefully, guys, that's helped you understand a little bit more about rates of reaction, and in particular higher tier and drawing tangents and using that to work out the rate of reaction. As always, if you've got any questions, please don't hesitate to email me or ask me when I see you in lesson. But hopefully that explains rate of reaction to you. And if that's higher tier, this is the last video in the series, and we've got 2 more to go for foundation tier. But that is us now covered every single topic for higher tier. All right, thanks, guys.